Hey everyone, and welcome to this explainer. Today, we're diving into one of the most fascinating and honestly absolutely crucial technology trends happening right now, the massive collision between artificial intelligence and cloud-native infrastructure. We're going to break down how the underlying systems powering our digital world are rapidly evolving to support the sheer mind-boggling scale of modern AI.
So here's the massive elephant in the room that the tech industry is facing. AI is brilliant, right? It's writing code, it's generating art, it's solving incredibly complex problems in seconds. But while AI is eating the world, it is simultaneously devouring our servers, our budgets, and our power grids. Training and running these models requires a staggering amount of resources. So how on earth do we afford to actually run this stuff without completely bankrupting companies or, literally melting our data centers? Well, the answer lies in fundamentally rethinking our infrastructure.
Okay, let's dive into this. We'll quickly walk through the AI infrastructure bottleneck, enter cloud-native AI, fixing the ML pipeline, high throughput and the edge, and finally wrap up with the future of CNAI.
All right, Section 1, the AI infrastructure bottleneck, when hardware just can't keep up.
Consider this number for a second. 18 months. The CNCF Cloud Native AI white paper points out that the data demand for building these models is actually outpacing Moore's law. It's doubling every single 18 months. This is creating a massive, honestly terrifying gap between the computational needs of data scientists and the actual hardware sitting in our server racks. We are literally pushing the limits of physics and hardware availability here.
Which brings us to Section 2. Enter Cloud Native AI, the elastic solution.
So the crucial point here is understanding what CNAI actually is. It stands for Cloud Native Artificial Intelligence. Basically, it refers to approaches and patterns for building, deploying, and scaling AI workloads using proven cloud-native principles. We're taking the exact same principles that totally revolutionized web apps, things like containerization and microservices, and applying them directly to AI. By tapping into the cloud's underlying compute, network, and storage, CNAI gives us vital isolation and controlled resource sharing. And that speeds up performance while critically driving down costs.
Now, the white paper makes a really important distinction between predictive AI and generative AI. Predictive AI, like a spam filter or a housing price predictor, has pretty moderate, batch-driven needs. General-purpose hardware can usually handle it just fine. But generative AI, that's a whole different beast. It requires massive, diverse datasets for training, highly elastic infrastructure, and intense computational power running on specialized, incredibly expensive hardware like GPUs. You absolutely cannot treat these two workloads the same way.
Moving right along to Section 3, fixing the ML pipeline, bridging the local and distributed worlds. Let's look at the standard machine learning lifecycle: data preparation, model training, model serving, and finally observability. The problem is, developers usually write Python scripts locally on tiny data sets. But when you try to push that over to a massive distributed production system, total synchronization nightmare. Take a company called Samsara, highlighted in the paper. Their pipeline was fractured across a bunch of microservices, which slowed everything down and made resource sharing a huge headache. By unifying the whole shebang with a distributed computing engine called Ray, they slashed their total yearly ML inferencing costs by nearly 50%. Unified infrastructure is, for sure, a real game changer here. And when we talk about cost, we've got to talk about GPUs. Think of a GPU like ultra-expensive, highly sought-after real estate in a major city. In the past, if an AI container needed a GPU, it basically took over the entire building, even if it only used a fraction of the space. But now we have DRA, or Dynamic Resource Allocation, a new Kubernetes API. DRA lets us fractionalize these GPUs. Instead of dedicating the whole building to one tenant, you just rent out the apartments. This maximizes usage and absolutely slashes wasted spend. That perfectly sets up Section 4, high throughput and the edge, taking AI directly to the user. Look, serving large language models is notoriously memory-heavy and slow, but deploying advanced frameworks like VLLM right on top of Kubernetes is a total fix. We're talking about utilizing cutting-edge techniques like page detention, which handles memory caches sort of like how an operating system handles virtual memory, plus continuous batching and optimized CUDA kernels. This means incredibly fast, high-throughput serving at a massive scale, keeping response times snappy even when millions of users are pinging the service all at once.
And this brilliantly illustrates what happens when we push all that compute out to the absolute edge of the network. Combine WebAssembly, or WASM, with Kubernetes, and you get ultra-low latency AI inference. With tools like SpinKube, developers are deploying WASM applications as Kubernetes native resources and hitting sub-millisecond cold starts. I mean, literally a fraction of a millisecond. Real-world partnerships like Fermyon and Akamai are already proving that WASM's secure sandbox execution delivers near-native speeds across hundreds of global edge locations. It's AI running right where the user is, almost at the speed of thought. Finally, let's wrap up with Section 5, the future of CNI, sustainability, safety, and automation.
Now, I want you to hear this quote from the CNCF white paper because it's a stark wake-up call. Training emissions are comparable to multiple transcontinental flights. The environmental impact of training these massive models is gigantic. The industry's obsession with oversized models is burning through power. But the cool part is cloud-native technologies are fighting back. Frameworks like K-Serve auto-scale resources dynamically, so we aren't just burning energy on idle servers doing nothing. Plus, pushing ML serving to edge locations powered by local, renewable energy is becoming absolutely crucial for cutting down that massive carbon footprint.
Alongside the environmental side, the white paper dives deep into trust and safety. When you're scaling this fast, you inevitably run into the risk of unintended consequences. The researchers emphasize the absolute necessity of something they call safety by design. Basically, proactively building systems that mitigate algorithmic bias and block malicious uses. Trust and safety teams are actually leveraging cloud-native infrastructure right now to scan for risks, manage content, and prevent the generation of harmful or illegal materials. It's really all about balancing that crazy fast innovation with actual public responsibility.
Which brings us to a final, kind of mind-bending thought. We've talked all about how Cloud Native supports AI, but now AI is actually supporting the cloud. Projects like K8GPT use large language models to let you talk to your cluster in plain English, helping operators debug and manage Kubernetes. We've got machine learning models analyzing usage patterns to predict workloads and optimize power consumption. So here's a question to leave you with. As AI continues to completely reshape the cloud, are we rapidly approaching the day when the cloud simply runs itself? Well, thanks for tuning into this explainer. Catch you next time. Keep learning and keep exploring.